Welcome and thanks for coming to this Science and Faith Examined event entitled Are Miracles Madness with Dr. Hugh Ross. This is the second of 7 events that are planned for this academic year here at Caltech. And it's great to see all you folks turned out at the first event and here at the second one. My name is Len Tang, and I'm one of the SAFE event organizers. I have through my parents, a many decades-long connection both to Caltech and to JPL, and I currently work at Fuller Seminary here in Pasadena. I'm leading a new church here in Pasadena as well. I wanted to let you know that this event happened through the work of many different partner organizations here at Caltech, and several folks have come and planned and labored and set up. So just want to again recognize some of those groups that are helping sponsor it. Caltech Christian Fellowship is led by John Lee, who you'll meet in a bit. Graduate Christian Fellowship is led by Jonas Lippenauer, and Bridges International is led by John Pang. So we're grateful to all those, and I'm the leader of Missio Community Church. Each of those folks on your table is a handout that has the information about the upcoming event in January, as well as connections to the existing fellowships that want to encourage these conversations to be happening on campus. And so you'll see there the meeting times for each of them, CCF on Mondays, GCF on Tuesdays, Bridges on Fridays, and actually Missio is having our first ever preview worship service tomorrow night. So all of us are trying to create spaces where people can explore their questions, their doubts, and the integration of science and faith. Now, the last sort of sponsor is this group called STEAM, which stands for Science and Theology in Emerging Adult Ministries. They gave us some upfront grant money that helps to buy your dinner, among other things. So we're grateful for that. That project is administered through Fuller Seminary here in Pasadena. Now, very briefly, since this is the first meeting of Science and Faith Examined since the presidential election, it was interesting. This past Thursday, there was an article in The Atlantic magazine entitled, "How Will Trump Use Science to Further His Political Agenda?" And the author, I thought, started out this way, saying, "Of all the memorable lines from this last year's election, the one I keep returning to months later is from Hillary Clinton's acceptance speech at the Democratic National Convention. 'And I believe in science,' she said. My Twitter feed that night was full of scientists and writers who had waited long to see science on the political stage. One of the tweets was, 'Hillary, science is not a belief.'" The writer goes on, though, to say, "We often make decisions emotionally, sometimes based on tribal affiliations. Then we marshal the facts to prove us right while discarding the ones that prove us wrong. As such, throwing more facts at, say, climate deniers hasn't convinced them. When Yale law professor Dan Kahan surveyed 1,500 adults about climate change, he found that scientific literacy did not correlate with perceiving climate change as a greater risk. Rather, higher scientific literacy made people more extreme in how they viewed climate change on both sides. Expressing a view on climate change is often a statement of identity more than anything else. That brings me to a troubling response I saw to Clinton's DNC speech, that science is not a belief. In theory, science provides an objective framework for finding truths about the world. I think that's what these responses were getting at. But in practice, science is conducted by humans with biases, often blind to them. To ignore how the practice of science is intertwined with politics is to be blind in turn to the coming changes." And so the author kind of encourages us to sort of be thoughtful in the way that science is used and viewed. And we want to be able to do that, to sort of think about the frameworks with which we're bringing to even our scientific inquiry. So that's really kind of the intersection of science and faith and worldviews, frameworks. These are ways that we're all trying to find truths about the world. So that's just by a way of introduction and provocation a little bit. Tonight's talk, again, if you want to take notes or questions or arise in your mind for the discussion to happen later, there are pens and again pieces of paper. So feel free to use those, jot down notes if you'd like. And here tonight to introduce tonight's speaker is Bijan Yamadi, who some of you met at the last event. Bijan is the project scientist for the Science and Faith Examined project. He's an astrophysicist. He's been a senior engineer at JPL for the last 15 years, and he himself has spoken for many years on the integration of science and faith. Bijan is also a visiting scholar with the organization that our speaker founded called Reasons to Believe. So Bijan, would you come and introduce them? Let's welcome Bijan.
Hi, everybody. It is a real pleasure and honor to this evening to introduce to you Dr. Hugh Ross. Dr. Ross is an astronomer and founder of Reasons to Believe, which is an organization dedicated to the demonstration of the compatibility of science and Christianity. He earned his bachelor's in physics from the University of British Columbia, and then went on to get his master's and PhD in astronomy from the University of Toronto. For several years, he continued his research on quasars, excuse me, on quasars and galaxies right here in Caltech. And at this time, he was the president of the foundation that he started, and that's called Reasons to Believe. And he's the author of a lot of books, including Navigating Genesis and Why the Universe is the Way It Is. By the way, there's a book table here with that, at least one of those titles right here. I'd encourage you to make your way to it after the talk. I have something to share, which is my own introduction to Hugh Ross was while I was a high-energy physics postdoc at Cornell. I was on an owl shift, and an owl shift was where you had to babysit the experiment from midnight to 8 a.m. And the two of us who were stuck with that job, the other guy was also a postdoc, and he had this blue book in his hand that he was going to, if there was a moment of relief from babysitting this thing, he was going to read, and it was called The Fingerprint of God. So I asked him about it, and then later got a copy, and it profoundly actually influenced me, having read that book. So tonight, Dr. Ross is going to talk to us about the many ways in which our universe appears to have been fine-tuned for bringing human beings into a relationship with God. So with that, please join me in welcoming Dr. Ross.
Well, thank you for inviting me here. I did serve here at Caltech as a postdoc and research fellow for 5 years, doing research on quasars and galaxies. And the organization I've founded, Reasons to Believe, what we do is we take academics like myself out of places like Caltech, where we get to enjoy interdisciplinary research. When I was here at Caltech, I really only could read the scientific literature that was pertinent to the research I was doing. But now that I'm no longer here at Caltech, I've got the luxury of reading across many different disciplines. And so that's what we do at Reasons to Believe, is we integrate across the different scientific disciplines and try to mine it for new reasons to believe in the Christian faith. And yeah, there was some discussion earlier about global warming. It's going to be part of tonight's talk here. And I'm really going to frame it in the context of what has happened in the recent history of the Earth. Now, the book on which this is based, there's these cards you can get at the table here. Encourage you to take one of those. It's just a quick summary of what we found to be the best scientific evidences for persuading people who have had no contact with Christianity that the Christian faith is scientifically credible and accurate. So take one of those. And we're actually giving away this DVD. And this is where I tell my story of how astronomy brought me into the Christian faith 8 years before I really got to know a Christian. I became a Christian in Canada. They're much harder to find up there than they are down here. And I really didn't get to know a Christian until I joined the astronomy department here at Caltech. So the first Christian I got to know was an astronomer at Caltech 8 years after I became a Christian. And he actually helped me to find a church. I couldn't find one in Canada because no one could tell me how to find a good one. So it took coming to Caltech for me to be able to find a church where people actually believe that the Bible is the inspired, inerrant Word of God. And this is the book I'm going to review for you quickly. It's just been out 2 months. It's been on the bestseller list for 6 weeks now. And I basically tell the story of how the entire universe, well, actually, to tell you a little bit of background on this, and hey, I need to set this up this way, excuse me. Okay, nope. Let me, just give me a minute here to go under, that's the problem. Okay, this should work now. Yeah, here we go. The birth of this book was 5 years ago, where in my church I was going through the different creation texts of the Bible, and what we notice is that every major creation text links the teaching on creation with the teaching on the redemption, and how you actually can see passages in the Bible that make the point that God begins his works of redemption before he creates anything. Now that would imply that everything we see in the universe, every component and every event in the history of the universe, the earth and Earth's life, plays a role in making possible billions of human beings being able to discover the existence of God and to form a relationship with that God. And so that launched a 3-year study of the scientific literature. And basically that's what this book is all about. It summarizes that 3 years of literature search, where we're basically making the point, yes, it really does seem like every event in the history of the earth, the universe, and Earth's life plays a role in making possible billions of human beings being able to discover God and come into a relationship with God, and likewise every event. In fact, we're recognizing this could be a powerful tool to more rapidly and more efficiently advance the march of science. That if we interpret nature from a redemptive perspective, we're going to be able to make more efficient scientific progress. So that's something that a lot of you can put to the test and join us in doing that. And the whole point is that it looks like the universe, Earth and Earth's life, has been purposely designed to make possible the redemption of billions of human beings in a relatively short period of time. Now, where you get this from a Christian perspective is several passages of the Bible, but this is one that I think is most specific, where it talks about the numbers of human beings that will be in a redemptive relationship, eternal relationship with the Creator of the universe. And it says it will be a countless number. Well, the Greeks at that time had a mathematics system where the numbers went up into the low billions. So this would imply that we're looking at least many billions of human beings discovering God and being able to come into an eternal relationship with that God. And what I'm going to do this evening is simply focus on 4 events. The book describes several hundred, but I'm only going to focus on 4, and 4 that are particularly the most recent. And one is that in order for us to even exist, our sun must be almost perfectly middle-aged, and that we have to be living on Earth when there's an ice age cycle, and we have to be at the end of that ice age cycle. We need to be living on the planet where we're in an episode of extreme climate stability, and one where no nearby supernova are exploding. So I think you can get an idea of why it takes an interdisciplinary approach to be able to develop this kind of a story. And let me begin with the sun. This is an area of my specialty, astronomy, and one thing we know about stars is they're a lot like human beings. What stars and human beings have in common is they're unstable when they're young, they're unstable when they're old. They're maximally stable when they're middle-aged. And in the case of stars, it's to a far greater degree than it is for us human beings. So, for example, this is what the flaring activity and the ultraviolet and X-ray radiation activity of our star, the sun, looks like. And to put this in perspective, stars that are identical to the mass of the sun have the least amount of flaring and the least amount of X-ray and ultraviolet radiation. So it's a good thing that our sun is the mass that it is. But it's also a good thing that we human beings are here when it's perfectly middle age. Now, that scale that you see on the left, it is logarithmic. So there's more than a factor of 1,000,000 from the bottom to the top. Now, if you're a bacterium, you can handle a little bit more radiation than you can if you're a human being. But the flaring minimum occurs when the sun is 4.57 billion years old. And about 7 years ago, the neutrino detectors that exist here on Earth were able to see from the neutrinos that they were collecting that our sun entered an extremely stable luminosity phase beginning about 50,000 years ago, and also that it will end in less than 50,000 years from now. And that's one of the requirements to have global human civilization, is that the sun have an extremely stable luminosity phase, and apparently that's only possible when the sun is almost perfectly middle-aged. Now, the sun changes in another way. It changes its brightness with respect to time. As most of you know, the sun is producing its light through the fusion of hydrogen into helium. But as it fuses more and more hydrogen to helium, it makes the density of the core of the sun greater and greater. And as that density goes up, it causes a nuclear furnace to burn more efficiently. And so if we were to look at the luminosity of the sun throughout its history, it would look like this. Sorry, we're missing the left side of the slide there. But it almost doubles in brightness as it accumulates mass. Then it stops accumulating mass. Then it actually begins to lose some mass. Then it stops losing mass. It stops losing mass when nuclear fusion kicks in. And then the sun slowly brightens over its history. So today, it's about 20 to 22% brighter than when life first existed on planet Earth 3.8 billion years ago. But you heard me say earlier, and I'm going to explain why, for global human civilization to be possible, you have to be living in an ice age cycle. And what we're going to see here is that it's going to be quite challenging to get ice on our planet, given how bright and warm the sun is right now. And the ice age cycle looks kind of like this, where you get a very brief period where only about 10% of our planet is covered with ice. We're in that period right now. And then you get about 90,000 years where you got 20 to 23% ice. And then you get another 10,000 year window where it goes down to only 10% ice. And we've had this cycle for the past 800,000 years, and only for the past 800,000 years. We're living at the only time in the history of the Earth where there's been an ice age cycle. There's been ice ages in the past, but not an ice age cycle. And only in the last 800,000 years have we had this cycle with a 100,000 year period. Now I'm going to briefly explain why you want to be living here during an ice age cycle. It's the only way you can grow enough food to feed billions of human beings at one time. Why? Because the melting of glaciers left over from the last ice age is what waters the great agricultural plains. I mean, think for a minute, the great rivers that exist here on planet Earth. The 20 biggest rivers that flow out of Asia, for example, come out of the Tibetan Plateau. And it's the melting of ice in the Himalayas and the Tibetan Plateau that feed the great rivers that water the plains of India and China and Southeast Asia. And likewise here in North America, we're still living off of the ice left over from the last ice age. You know, I'm a Canadian, so I hike a lot on the Canadian ice fields and glaciers when I get a chance, just because they're really beautiful. But it's the melting of that ice that feeds the Mississippi, the Missouri, the Columbia, the Fraser, all the great rivers of North America literally come out of the melting of ice left over from the last ice age. And so if we're to go back into the last ice age, this is what it would look like. That blue that you see there shows you those parts of planet Earth during the last ice age where you got at least 1,000 feet thickness of ice. But for example, what you see here in North America is that edge is basically showing you where you got 3,000 feet of ice. The Ice Age actually came all the way down here into California. For example, Yosemite was carved out by the last Ice Age. But as the ice retreats from the last Ice Age, it exposes high altitude plateaus, and it causes a powerful wind to blow off those plateaus, and that actually fertilizes the Great Plains of North America, South America, and particularly India and China. And so they benefited from the wind blowing this fertile dust off the high plateaus and dropping it onto the agricultural plains. And so thanks to the fact that we're living in a period following actually the most intense of the ice ages in the Ice Age cycle, explains why we're able to grow as much food as we are able to do and literally have billions of people living here at one time. Very quickly, I'll take you through some of the other benefits of living in an Ice Age cycle, namely that the retreat of the great glaciers carves out lakes all over Russia and Canada, and also carves relief so that you got waterfalls flowing off these high plateau areas and dropping into low, and that allows us to have hydropower. And in Canada, for example, they get virtually all their electricity from hydropower. Again, thanks to the fact that we're living in an Ice Age cycle. Speaking about Canada, it possesses half of the lakes. More than half the world's lakes are in Canada, and they're all carved by the retreat of ice left over from the last Ice Age. Here's a blow-up of Quebec, for example, which gives you an idea just the extent of the rivers and the lakes there. And it's because of that extensive network of lakes and rivers in Canada and Siberia that those areas of the world are heavily forested. If it wasn't for those lakes carved out by the last Ice Age, Canada and Siberia would be deserts. They only get 10 inches of rain a year. And because of their all the lakes there, even though they only get 10 inches of precipitation, it's enough to sustain very productive forests and the ecosystem that's there with it. Some other benefits: it produces large alluvial plains, which allows you to grow more food, exposes rich ore deposits, forms large safe harbors through the fjords, and it also creates spectacular scenery. Believe it or not, we're living at the most scenic time in the history of planet Earth. Never before have we had such spectacular scenery, and I think our Creator knew that we needed the relief from being able to escape a place like Los Angeles and be able to go to a place where you can kind of spiritually recover from the stress of living in a city. But as I mentioned before, ice is rare in the history of planet Earth. For 90% of Earth's history, it had no ice at all, no polar caps, no ice anywhere. And when we did have ice, it was ice that stayed around for millions of years. And moreover, it kind of looked like this. We're not just talking 20% of the planet being covered with ice, but we're talking 50, 60, 70, and in this case, 90% of the planet being covered with ice. Now, there are some papers written 10, 20 years ago that talk about Earth having an ice ball event where the entire planet was covered with ice. That's now been recognized not to be correct. Our planet always had regions where there was no ice. But one of the events could have covered as much as 90% of the planet. But here's the, let me go back to this slide here. What you notice here is that, yeah, we have these brief episodes, millions of years, where you got ice, but there's only one very tiny sliver of time where you got an Ice Age cycle, and that's right now. So never before have we had an Ice Age cycle. And the paradox of all this is that we're having this Ice Age cycle when the sun is way too bright for that to be possible. So this has been a problem in the scientific community. How do we explain the fact that Earth right now has ice when the sun is as bright as it is? And then also, why is it cyclical? Well, we have an idea why it's cyclical, something called the Milankovitch cycles, where we realize that the orbit of the Earth has slight variability. It's the shape of its orbit varies. So, for example, the elliptical shape becomes more or less elliptical with a period of 100,000 years. And then the tilt of the orbit has a variation of 41,000 years. So for about a 2 million year period, we had an ice age cycle of 41,000 years. It was driven by the variation in the tilt of our orbit. But that meant the warm interglacials were only 2,000 years long at most. And what happened 800,000 years ago is we transitioned from a 41,000 year cycle to a 100,000 year cycle. And again, that's because of the shape of the orbit. But what I want to describe next are 5 simultaneous, unprecedented tectonic events that allowed our planet to have ice when the brightness of the sun would dictate we should have no ice at all. So 5 simultaneous, unprecedented tectonic events worked together to cool our planet enough that we could have ice when the sun is as bright as it is. And of course, it must be that bright if we want to have human beings, because we need the sun to be as stable and to have as little ultraviolet and flaring activity as it has. So the first of these events is what happened to Antarctica. Antarctica was attached to Australia. It broke off from Australia several tens of millions of years ago, but remained attached to South America. And about 10 million years ago, it broke off from South America and began to wander towards the South Pole. What's interesting, as soon as it became centered on the South Pole, it stopped moving. So here it is over the South Pole. And that alone was not enough to cause ice to form over Antarctica. But what happened, as you can see in the next slide, is that we now have a continent separated on all sides from other continental land masses. And so this allowed the circulation of ocean water around Antarctica and also powerful winds. Those of you who have read sailing novels may have heard of the Roaring Forties. These are 40-mile-an-hour winds that race around Antarctica nonstop, and also generates powerful ocean currents. And those powerful ocean currents and winds work to cool Antarctica and also cause enough precipitation to fall that ice began to accumulate. So the ice we see in Antarctica is relatively recent. But ice, unlike open ocean water, reflects sunlight quite efficiently. And so the covering of Antarctica with ice reflected away enough sunlight that it had a cooling effect on the planet. The other big cooling effect is that powerful ocean circulation around Antarctica absorbed huge quantities of carbon dioxide. And that ranks still today as one of the biggest carbon dioxide sinks on planet Earth. And so pulling carbon dioxide out of the atmosphere, thanks to that powerful circulation, also worked to cool the planet. The other thing is that that powerful circulation sent cold water running up the Atlantic Ocean. And so it worked to cool the Atlantic Ocean and the land masses next to the Atlantic Ocean. Okay, that's one tectonic upheaval. The second one is what happened to Greenland. Greenland, a few tens of millions of years ago, was situated off of where Newfoundland is today. But it began a rapid tectonic northward movement of 1,100 miles. And as it moved northward 1,100 miles, I mean, consider this. The northernmost landmass on planet Earth today is the northern tip of Greenland. However, when Greenland was down around where Newfoundland was, it was a low landmass. It didn't really have any elevation above about 1,000 feet. But as it moved northward, it moved over a plume hotspot. And that upwelling from the mantle caused the landmass of Greenland to go from a few hundred feet to many thousands of feet, where now you got a lot of the landmass of Greenland above 8,000 feet elevation. And so the rise of the Greenland landmass and its northern location caused ice to form over Greenland, even during a warm interglacial. And again, ice reflects sunlight a lot more efficiently than bare ground or vegetation, and that worked to cool the planet to some degree. And just like with Antarctica, once it got to that position, it stopped moving tectonically. Now, another major tectonic event is what happened to the great continents. A quarter of a billion years ago, we had a supercontinent Pangaea. It split apart. It's still splitting apart. But what's unusual about this cycle of the breaking up of the supercontinent is that we have a lot of landmass moving towards the north. As this doesn't show it too well. Something is happening here. Oh, we got to back up here. Great. Okay. So, did everybody get to see Greenland before the projector popped out? I wasn't looking at the slide. So, if I go back one, yeah, that's kind of what happened to Greenland. Okay. So, all right. Yeah, we should have done this in the first. Yeah, no, should have been on us the whole time. Even the colors are good. So, this is great. Thank you. Well, that was tectonic event number 2. This is number 3, where we have the breaking up of the supercontinent. But what you notice is most of the land mass of planet Earth today is now in the northern hemisphere. But it's also clustered around the North Pole and has almost completely enclosed the Arctic Ocean. And it was that near enclosure of the Arctic Ocean that allowed the polar ice cap to form, because continental land masses at that latitude are much colder than the open water. And so the proximity of the land masses is what led to the formation of the polar ice cap. Just like the ice cap over Antarctica, the polar ice cap is a relatively recent event. It's only been there for a few million years. But now that we have the Arctic Ocean covered with ice, it reflects sunlight more efficiently and works to cool the planet. Okay, tectonic event number 4 is what happened to North and South America. You go back 10 million years over at the left, you got a large channel of open water connecting the Pacific Ocean with the Atlantic Ocean. And the problem here in terms of trying to cool the planet is the Pacific Ocean water near the tropics is very warm. And so 10 million years ago, you had this flow of warm Pacific Ocean water into the Atlantic, which blunted the cooling of the Atlantic Ocean due to the circulation coming up from Antarctica. But 3 million years ago, we have the formation of the Isthmus of Panama, where North America now becomes joined to South America. And that put a stop to the flow of warm Pacific Ocean water into the Atlantic. And, we even have the whole slide now. This is so much better. I'm very impressed. So I don't have to tell you what's on the left anymore. But the formation of the Isthmus of Panama 3 million years ago had a major cooling effect on the oceans of the world. And it's kind of what it looks like now. And so we actually have a barricade separating the Pacific Ocean from the Atlantic Ocean. But the most dramatic and most important of these tectonic events is what happened to India. If you go back 70 million years ago, India was attached to the island of Madagascar. Then it broke off from Madagascar and rapidly sped towards Asia. In fact, this ranks as the most rapid tectonic movement in the entire history of the Earth, measured at 22 centimeters per year. You say, that doesn't sound too fast, but that's about 11 times faster than normal continental tectonic movement. And so the fact that it was moving at such an extremely high velocity meant that when it hit Asia, the collision resulted in ocean seafloor matter being pushed up and forming the Himalayas. I mean, if you were to climb the Himalayas today, you'll notice there's seashells at the top of the Himalaya Mountains. Well, for good reason. The Himalaya Mountains are pushed up seafloor material that was between Asia and India. Now, the second fastest plate tectonic movement that's been recognized in geophysics is the speed at which India is continuing to crash into Asia. It's moving at 5 centimeters a year. So even now, it's still pushing northward into Asia, which is causing the Himalayas to get higher and higher and the Tibetan Plateau to get higher and higher. In fact, we now know Sir Edmund Hillary did not climb the world's highest mountain. Mount Everest today is 1.5 feet higher than when he climbed it. And for interest's sake here, the second fastest mountain uplift in the world today is just a few miles from here. The San Gabriel Mountains rank as the second highest tectonic uplift in the world today, about half of what the Himalayas are rising up. But it was this dramatic crash of Asia into the, or India into the Asian continent that caused the Tibetan Plateau to be pushed up to an average elevation today of 17,000 feet. And so the biggest store of ice on planet Earth today is Antarctica. The second biggest store of ice is Greenland. The polar ice cap does not rank third. What ranks third is the ice over the Tibetan Plateau and the Himalayas. That's the third largest store of ice. But the reason this has such a dramatic impact in cooling the planet, we have this huge area of ice at a low latitude. And because of its low latitude, it's 4 times more efficient at reflecting sunlight back into outer space than the ice over Greenland and Antarctica and the polar ice cap. And so this has the biggest cooling effect on planet Earth today. And the idea that we have that huge quantity of ice so close to the equator explains why we have this ice age cycle. It also explains why in the last 8 episodes of the ice age cycle, each successive ice age has been more severe than the previous one. Why? Because the Tibetan Plateau is continuing to rise. And so with every ice age, you get a bigger coverage of ice over the region of Tibet. During the last ice age, over 1 million square miles were covered with ice. And the next one that comes, it will be even a bigger area of ice that will be covering. And so with each ice age, you get a little more of the planet covered with ice, and the ice is a little bit thicker. Let me make a little change here. There we go. Okay. Now, what drives the ice age cycle there's actually 7 different variations. These are the 4 most significant. Oh boy, let me pull this up here. This is all supposed to be set up before we got going, but let me, okay, what's going on here? Come on. Here we go. Now, I don't want to join Caltech, yes. I simply want to mirror this. There we go. Okay. All right. So these are the 4 most significant cycles that explain why we have this variation from 10 to 20% ice. But this is what it looks like. This is from the reconstruction of the temperature of the planet based on what we see in Antarctica. But we actually have ice cores in the Alps as well as in Greenland that show us that indeed this accurately represents the global mean temperature of the planet. And so what you see is a temperature in degrees centigrade on the left and the temperature of planet Earth throughout the last 4 ice ages. And what you notice is that you get a period of about 90,000 years where the planet is about 20% covered with ice, and then the planet rapidly warms, hits a peak, and drops back down. This is about 10,000 years wide. This is about 90,000 years wide. But what I want you to notice is that throughout the entire ice age cycle, this shows the last 400,000 years, but is representative of the last 2 million. We have the temperature, the global mean temperature, varying on very short time scales. In fact, this is a blow-up of what it looked like during the last ice age. And you can get an idea just how rapidly the temperature was jumping up and down. And in terms of degrees Fahrenheit, we're looking at 24 degrees Fahrenheit variation in the global mean temperature. Now, we have evidence that humans were attempting to launch civilization during the last ice age. In fact, papers had just been published in the last year showing that people living 20,000, 30,000, 35,000 years ago were actually roasting grain. They were gathering grain, roasting grain, grinding the grain, and using that to make pastries and bread. But it was all done on a very small scale. Such a small scale that only in the last year have we found evidence that this was going on. And also noted that they were actually planting grains and harvesting grains, but again, on a very small scale. So it's actually changing the textbooks in anthropology, where the idea was that the early humans were only hunter-gatherers, but now we realize they were actually engaged in fairly sophisticated agriculture. But it was all on a very small scale, and also they were growing multiple crops. Now, with a temperature jumping up and down this dramatically, a farmer would have no idea which crop was going to fail and which crop was going to produce food for his family. So what we now know is that they were typically planting 10 to 15 different crops on 2 or 3 acres, and maybe 8 of those crops would fail, and they would feed their families on the ones that made it. But they would have no idea which ones were going to make it and which ones weren't. And that was the status of humanity, and explains why the human population was so low during the last ice age. The climate was so unstable, it was impossible to develop the kind of food production that would be necessary to sustain a large population, and also made it impossible to grow a sufficient surplus of food that you could take a fraction of the population and say, you're going to do engineering and science. Everybody had to be engaged in producing food. And so, for example, you go back during the last ice age, at least 95% of the population was engaged in simply trying to produce enough food. Whereas today, I think the figure in the United States is only 1% of our population is engaged in producing food. The rest of us have the luxury of doing engineering and science. And explains why, for example, you have what's called the Neolithic Revolution. With the close of the last ice age, we see this incredible advance in technology. And that technological advance has been sustained to the present day. Now, what has made possible our planet being able to sustain billions of human beings with a high enough level of technology that we can understand the message of redemption that the creator of the universe is communicating to us and respond to that message is because of what has happened in the last 9,000 years. What has happened is it's 7 different cycles in the variation of Earth's orbit and the rotation of our planet have come into sync to produce this unprecedented window of extreme climate stability. So for the last 9,000 years, the global mean temperature has not changed by more than 2 degrees Fahrenheit. And because of that extreme climate stability, we've been able to specialize our agriculture. I mean, that's what we noticed. Starting about 10,000 years ago, humans for the first time began to specialize, where one group of farmers would do nothing but raise goats. Another group of farmers would do nothing but raise wheat. They could afford to do that because the climate was sufficiently stable that they could plant several square miles of wheat, for example, and know that they would get a very productive harvest from all those wheat fields that they had planted. And that's what allowed humans for the first time to produce a surplus of food and therefore be able to devote a significant fraction of the population to arts and science. And that led to a rapid advance of technology, trade. People began to live in cities and villages. And that led to what we have today with 7.5 billion people on the planet enjoying an unprecedented standard of living. Even the poorest nations of the world have seen a dramatic increase in the standard of living. But what I find paradoxical as a scientist is how we have that extreme climate stability when we're in an ice age cycle. The ice age cycle, you would expect that the temperature would be jumping up and down by 24 degrees Fahrenheit. Indeed, that was the case for 2.5 million years. Only the last 9,000 years have we had this period of extreme climate stability. Now, a question I often get asked is this: how long can we continue to sustain this period of extreme climate stability? Not much longer. We know those cycles are coming at a sink. There are things we human beings can do to try to stretch it as long as possible, but we're talking at most stretching it by a few centuries. We're not going to be able to stretch it by thousands of years. One model I've seen, we might be able to push it out as much as 1,300 or 1,400 years. But then the Milankovitch cycles will bring it to an end. And matter of fact, in one respect, those cycles were ready to take it out of sync long before the present. But it's thanks to human activity that we've been able to sustain this period of extreme climate stability. Now, of course, we can overdo it. And what's interesting is when you look at this thing here, right now, we're 3 degrees centigrade below that peak point where the temperature rapidly drops into a next ice age. And if the expectation is that if we warm the planet by another 3 degrees centigrade, then that will put us past the tipping point and we're going to rapidly drop into an ice age. You say, how does that happen? Well, there's a lot of different models out there explaining why when the temperature goes up 3 degrees centigrade above where it is now, you rapidly drop into an ice age. One thing we can tell you is, look at the past history, it's always happened. Why wouldn't we expect it to happen in the future? But there's actually some models that explain why that would take place. So for example, in my lifetime alone, half of the polar ice cap has melted away. And if we melt all of the ice cap away, you now got exposed ocean water to the sunlight impinging the Arctic Ocean. What is that going to do? It's going to cause more water vapor to be evaporated than if it were all covered with ice. And the greater evaporation of water means you're going to get more snow falling on Canada and Siberia. You know, I was raised in Canada. I can tell you, if you raise the temperature of Canada by 10 degrees, but double its rainfall, you're going to get thousands of feet of ice. I mean, changing the temperature from -60 to -50 isn't going to make much difference. If you've got enough precipitation, ice will form and it will accumulate. And so this is probably the leading model to explain why global warming quickly leads to global cooling, because you wind up getting more snow falling on Siberian Canada. In fact, one paper has been published claiming that we may already be seeing the first sign of the onset of the next ice age. Because in previous ice ages, the signs that you see before the next ice age begins is an accumulation of snow over western Siberia, followed by an accumulation of snow in Labrador. We're already seeing the accumulation of snow in western Labrador. We're not yet seeing it, or pardon me, in western Siberia. We're not yet seeing it in Labrador. And so previous studies of previous ice ages tell us you don't know for sure it's going to happen until it also happens in Labrador. So as long as snow is not accumulating in Labrador, I wouldn't worry about your stock portfolio. But once Labrador becomes covered, increasing amount of snow, then you need to worry. But this is why I think it's so important to do interdisciplinary research. This 9,000-year window we see here of extreme climate stability is identical to the window of no nearby supernova eruptions. And so this is what a supernova looks like, down there at the left. And it's a giant star, when it goes supernova, for a period of few months, will shine as brightly as several 100 billion stars. So it's a dramatic event, and they happen at an average of about 3 per century in our Milky Way galaxy. And a paper got published a year and a half ago documenting that there were 23 supernova that exploded closer than 1,000 light years during the last 300,000 years. And actually is making the point that's the norm for the history of the Earth. In fact, if you go earlier in Earth's history, that number would be higher than it is right now. But over the last several tens of millions of years, this would be the average, that you get roughly about 23 occurring every 300,000 years. And so what you see here in this table are the nearby supernova that exploded when humans first began to walk the Earth. And so, the dates we have, undisputed dates for the origin of humanity, is about 50,000 years ago. And so during the latter part of the last ice age, humans experienced 4 of these events. Now, we're talking 360 to 820 light years away. That's not close enough to kill off the human species. It is close enough to cause some health issues, but the most damaging part is what it does to agriculture, because the ultraviolet radiation from these nearby supernova would really stunt the productivity of vascular plants. However, once we enter this period of 9,000 years of extreme climate stability, no nearby supernova. These are the nearest supernova to the Earth, and notice none of them are closer than 5,000 light years. Far enough away that it has no impact on human health, and it has no impact on our agricultural productivity. But again, it's the only time in Earth's history where we can say there has been such a long period with no nearby supernova eruptions. The fact that it's identical to this period of extreme climate stability tells me this is not just an accident of nature. This is something the Creator planned from before He created the universe, so that billions of us could live here at one time, developed a technology where we could all understand that this God exists, and this God wants a relationship with us, and also enables us to take the message of how we can come into that relationship with Him. And that's kind of the last chapter of this book, Improbable Planet, how nature actually reveals exactly what that redemptive message is, and how that is now being communicated to billions of human beings, so that in fact the universe can make it possible for billions of us to have this eternal relationship with our Creator. Now, this is basically a setup for you to engage in questions. I've raised enough controversial issues here that I think it can lead to some fertile discussion around the tables. And that's really what this event is all about, is to get you dialoguing and discussing these things amongst yourselves. But if you got questions you want to pose to our scientists team at Reasons to Believe, each of us maintains a Twitter site and a Facebook page where you can do that. And we basically reserve our Twitter site for alerting you to the latest scientific research papers that have faith science significance. And we're recording an average of about 10 plus per day. And so we give you quick notifications of these and give you the link so you can read the papers for yourself. But yeah, we love to engage you with questions. I'm going to be around here for the rest of the evening to help with your discussions around the tables. So yeah, if I see things lagging on one of the tables, I'm going to come by and pose a controversial question and walk away. So I don't know if there's any other announcements you want before you engage in these discussions. So Bijan, did you want to say anything before we get going? Not really. Okay. All right.
Thank you, Hugh Ross.
Okay, so now, as Hugh Ross has stated before, now is the time for discussion questions. So we've split you guys up into these tables, and these represent your discussion groups. And each of these groups will have a discussion leader. So can discussion leaders please raise your hand? If you guys don't have a discussion leader, I'm sure either one of these leaders with their hands raised will be welcome to take you in. And before we begin this discussion, I would like to lay out some 3 ground rules. The first one is that we are all here gathering to learn more about how science and faith interact. And likewise, we have a lot of different backgrounds. So I ask that everybody is respectful of other people's beliefs and opinions. The second one is that you are not obligated to talk if you're just here to listen, if you just want to know more about one or the other side of this issue. So do not feel obligated to speak, only speak if you wish. And the last one is, if someone is speaking, I ask that you do not interfere. It would promote good discussion amongst the group if everybody were to listen when someone is speaking. I will be back up here at 8:10 for a 5-minute warning, and the discussions will go until 8:15.